All right. For those of you who don't know me, I'm Doug Newcomb with the U.S. Fish and Wildlife Service. And Dr. Petrus is over here in the front row. Dr. Petrus, I have to keep getting used to saying that. The three folks on the side here are field biologists who are out working today. I added them at the last minute. You won't see them on the program because it has some fairly interesting slides from their data. So let's go ahead and get started. Okay, if you don't know anything about LiDAR, just remember it's all done with mirrors, literally. You have a laser in a plane, you fly it over the countryside, you shoot a laser beam out, it bounces back, measure the distance, you end up with a point cloud, X, Y, Z, and a few other attributes as well. For the state of North Carolina, they've collected 360 billion points approximately in the 3 phases in the eastern 59 counties of the state. That's the data set I was working with. Phases 4 and 5 are going to be either 8 or 30 points per meter. That's the western part of the state with a different type of LiDAR, but it'll work fine with the methods I use. The key enhancements to GRASS 7.2 and beyond that Vashik did that really made this possible was to set up the GRASS RN LiDAR program so that you can use a base raster and do a height above ground on the fly based off the values of the base raster. And the base raster can be at a finer resolution than your final product as well. It corrects at the fine resolution and then goes ahead and does the calculation. It sets up the height above ground, and then you can do your statistical analysis from that. The other thing was that he enhanced it by saying, okay, here you can give this command an ASCII text list of LiDAR tiles, and it will process them as if it were one single point cloud, seamlessly. The workflow was generally along the lines of you take all the DEM tiles for a county, merge them into one raster layer, and then set up your workspace and to a common statewide blank, so every cell would align for every county as you processed it. You processed all the counties for canopy height or point counts to do percentage of points, and then you merge them all into one big layer and start looking at the statistics for the features that you are interested in across the whole area. So this is what the canopy height looks like. You can see the lower Roanoke has its nice big trees down there. You have the lack of data for Fort Bragg and Camp Lejeune. For some reason, they didn't want to give point clouds out for that. And you can see open ground farms there and some of the big farming areas in the east and the whole farming belt there in yellow for no canopy height. You can also, that previous raster layer is about 7 gigabytes. If you want to get something that's a little easier to work with, you can go to an integer raster and you just classify it using the Department of Agriculture's classes for heights versus type. Subshrub is 0.5 meter to 1 meter, shrubs 1 to 5 meters, and then I just broke that down to classes at every 5 meters. And since they classified the building points, I went ahead and pulled out and created a buildings class for that as well. You can use that for masts later on. The height classes and buildings, you can then just take this class and you can get the breakdown of every class type within each 12-digit HUC if that's of interest to people who are doing hydrologic modeling. Or you can go ahead and say, well, let's just get the volume of vegetation within each hydrologic unit. So you can compare different hydrologic units that way. You know, you've got the height, you've got the cell size, make a volume out of it. Then you can also make it a little simpler and go to a forest, non-forest, where your buildings are non-forest and anything below 5 meters is non-forest and everything 5 meters and above is forest. And that allows you to do analysis of fragmentation. There's an forest frag in grass that I've done, and as you go in different neighborhoods doing the fragmentation, it makes your edges thicker, which is kind of an advantage because you can start looking at how thick at an edge a different bird species might need. And if the biologist says to you, well, this species needs to have 100 acres of contiguous habitat, then you can just go through and do an area analysis on the core areas at the different segments and say, okay, well, here's our different core areas, and you can see that this area, it's connected because it's probably a power lines coming across here. But the 5x5 and the 7x7 give you more realistic core areas to work with. And then you can say, well, this is what 1,000 acres looks like for core areas at the 5x5, and there's a 7x7. So that gives you a way of looking across the landscape for contiguous areas of habitat. Then you can take this and break it down further by different needs. And then got the NLCD out here. Hi, Nate. I decided to compare this to the 2011 NLCD. Took the forest, no forest, and put the buildings back into it. So you had forest, no forest, and buildings, and just was doing a straight R report overlaying the two of them. And if you look at the developed areas, it comes out pretty well. As you increase the buildings, you know, the buildings percentage rises and the forest percentage drops, and the open space area rises, which is what you kind of expect. Works out pretty well. And for the forest, you get, you know, in the upper 80% of the forest is actually forest. That works out pretty well. You have natural clearings. One thing I found was interesting was that in the shrub scrub, most of it was actually forest. And if you look down at the grassland herbaceous, almost half of it's forest. You look at the pasture hay, over half of it's forest. And then cultivated crops, almost half of it's forest as well. So just by vegetation height, we've got some interesting differences there. If you look at the woody wetlands, that's actually pretty good. Herbaceous is about a quarter forest. And I think some of this is what you're getting. You know, the forested and developed, that works okay. The shrub scrub, I think trying to pull out something that the forest shrub, like it might be asking a little too much of a single cell, single pixel analysis. The agriculture areas, what I'm thinking is happening there is you've got your windrows in between, and the grass signature is probably overwhelming the tree signatures coming out of that. But, you know, remember, you're also talking about a 30-meter pixel versus a 6-meter pixel. And as if you watched Nate's presentation yesterday, it makes a huge difference having a higher resolution. But I'm look forward to the NLC 2016 because supposedly they are accounting for some of the LiDAR data, and we'll see how that works with it. Skewness, you look at the way the points are distributed vertically. In this case, the points, if the points are all towards the top, it's a negative skew. If they're towards the ground, it's positive skew. And if they're middle, things are pretty evenly distributed. And I'm sorry. You can see over here, you've got a lot of mid-story up there. You've got some areas where the yellow, a lot of that is actually plantation pine. And that pine plantations, they tend to have more density at the top. And then you've got other areas that are shrubby. Then we have the Z-ray restriction is useful in that you can look at just parts of the vertical cloud. So in this case, I went to counted the points 1 to 3 meters above the ground, and also counted all the points above the ground up to 250 feet, divided, and I get a percent. And you can see, oops, and I've gone too back. Okay, and you can see that the very shrubby areas over here and down and through here, the coastal areas are popping out quite nicely. And then if you can see the higher mid-story areas that you get in the Piedmont as well. So that gives you another pattern that you can look at. The fun thing about R and LiDAR using the base raster is you can use the digital surface model, look at from the top of the canopy and down into the canopy. So in this case, I'm looking at the top 3 meters of the canopy, and it's using the intensity measurements. This illustrates why you don't want to use intensity on the landscape scale, because it's not a calibrated metric. If you like quilts, then go ahead, be my guest. Bird species. We are Fish and Wildlife Service. We like birds. So now we start taking point locations from different databases of these birds. Natural Heritage Program database and the GBIF database, which is basically eBird plus some scientific data as well. There's 2 different goals between these things. We do a 25-meter buffer around the point locations because, well, that's what the cool kids do. And everybody else is doing it. And Natural Heritage Program, they're different. In the Natural Heritage Program, is looking at nesting locations. GBIF is wherever people see it, whatever time of the year. And you can see that in the data. Black-throated green warbler, GBIF has it as a fairly low canopy height, but natural heritage has a much higher canopy height. And the same with the red-cockaded woodpecker. You see the definite differences in the data. And if you look at the canopy height species, you will see differences even in the GBIF data. You'll see more marked differences in the natural heritage data. Like the painted bunting, for instance, that's a shrub nesting species. And you can see it has a very low mean canopy height. Henslow sparrow likes areas that are mixed open and tree. The one thing I want to talk about here for Swainson's warbler is that likes tall trees with an understory of giant cane. And you're actually seeing that in comparison to the other data, the other species. And then you look at the percentage points, 7 to 3 meters, you still see some differences. But then we get back to a single species. The advantage of doing a landscape data set is you can start to look at the differences in the species habitat across the geographic range. In this case, we're looking at the northeastern North Carolina up around Alligator River and Coastal Lakes, Sand Hills, Onslow Bight, and Boiling Spring Lakes, where there are known concentrations of birds. The one thing you see, the canopy height and that's the percentage and the skewness, 1 to 3 meter and skewness, is that northeastern North Carolina sticks out like a sore thumb. Everything else is pretty much, except for a little thing with Boiling Spring Lakes and the percentage. The other three are pretty close, but that one is sticking out like a sore thumb. Well, this is classical red-cockaded woodpecker habitat, thanks to the people at J. Carter and Associates for the photo. Frequent fires, minimal understory, nice herbs down here, and you can see for a while underneath there. Unfortunately, red-cockaded woodpeckers don't read the classical literature, and some of them nest in these areas, where you've got a very dense shrub layer with trees sticking up above it. But if you spend a few times looking at that, you'll notice that there's just sort of a shrub line right there. You take that shrub line, you can go back and do a high-resolution digital surface model of the vegetation in that area, and then we'll do a geomorphon analysis to pull out the flats, depressions, and valleys. There's our geomorphon analysis for Tyrrell County. And I'll just pull out anything, you see the blue of the valleys and such, and I'll pull out those areas that are in those three classes that fall between 8 and 16 feet above ground. And then I'll interpolate the elevations from the DSM between them so that you have a single plane cutting across that. And then you reprocess the point cloud using that as your base raster layer. And if you look at that, you've got a newer canopy height here based on above the shrub line for Tyrrell County, and then there's your skewness. And then we take nesting cavity tree locations for the red-cockaded woodpecker. We've got a couple of hundred up in Tyrrell County in 2 different groups, some from Boiling Spring Lakes and lots in the Sand Hills. And then you do the same summary statistics that we did across the entire landscape. There's our locations, in case you're serious. We didn't have the time to get the Onslow Bight ones. And if you look at the Boiling Spring Lakes canopy height for those cavity tree heights, and then you look at the above the shrub areas, you'll find that they match up almost exactly. So you go for as far as canopy height, you've got the canopy height above the shrub line for them to work. The Sand Hills is a little higher canopy height. Now, if you look at the skewness, the Boiling Spring Lakes is a little bit negative skew, but the above the shrub line, not quite, but it was very close, the Sand Hills skewness. Even though you've got taller trees, you've got a fairly close skewness to that. And the relative density above the shrub line actually didn't change that much. I was kind of surprised by that. But the thing is that you can use this for several different metrics. You know, you can process the LiDAR across the landscape. It's fairly straightforward to do. It's just a matter of, writing a Python script and say, you go do that for a few days. And then you can take the species locations across the geographic range, and your values of species can be extracted. And then you can segment the cloud if you see some things that, why is the species occurring here? It's not what I'm expecting. So next steps, I've got to log into the USGS Yeti supercomputer. I'm going to try to start scripting these out to process on that, and then hopefully we can try to move to other states and get it processed to get a more broad landscape wherever there's LiDAR data, to get some generic products out of it. I want to start cranking on the Western North Carolina data as it becomes available. And I want to get better, try to neck down some of the species data in GBIF to get it thinned down to get more species locations out of it. And please do try this at home. There's a nice tutorial on the Grass Wiki that tells you exactly how to do this kind of analysis of the point cloud and grass. And it's set up to do it in Windows, so not everyone has to compile in Linux. You download the grass software. And then I want to thank a lot of people I work with, the Department of Public Safety, giving me the LiDAR data, the grass folks, they're awesome, Natural Heritage Program, and J. Carter and Associates. And that's just data sources for if you want the PDF. Okay, does anyone have any questions? Yes?
Hey, Doug, I would expect when you were showing the differences between scrub, land cover, and the four sites measured by LiDAR, I think you would probably expect that based on like 3 to 4 years of growth of the scrub land.
Yes, I would agree with that. However, you will probably want to come to the presentation this afternoon, which had some 2010 data which showed some of the similar patterns. So I think it's more of a thing of it's just problematic. Yes?
I noticed your interest was mainly the high veg on the trees. What about the medium in the middle of the trees, middle of the foliage?
Well, that's why I did want to get the percentage of points that fall in the 1 to 3 and 3 to 7. If I go back and do it again, I'll probably split it up to 1 to 3, 3 to 5, and 5 to 7 to get it a little more segmented, to get that break. 1 to 5 meter is the shrub definition, and then I want to get that early mid-story stuff as well from 5 to 7. Breaking that out separately, I think, would work better, and that would give you more of an even split. Yes?
I guess the skewness gives you a little bit of that too. Skewed towards the middle.
Have I seen, I'm sorry.
Have you seen that pattern within the data as far as the skewness, which way it's skewed?
I haven't examined the data, but it's close enough to really, I'm sorry. The question is, and I'm supposed to be doing this for the recording, sorry. The question is, have I seen the pattern in the data to have a skewedness between the 1 to 3 and the 3 to 7? And I haven't examined it closely enough yet. And for those listening at home on the video that this may be, just email me and ask me about what the questions were. Anything else? Okay, go forth. Grab grass. Process LiDAR.